Good afternoon, students. Welcome to today's session. So we were discussing last time about the kinematics of SHM, and we had seen the method of understanding SHM as a projection of uniform circular motion in solving particularly complicated problems related to phase, initial phase constant, and those kind of things. So let's progress from that point onwards in today's lecture. So having completed the kinematics of SHM portion, understanding all the various kinematical parameters like displacement, velocity, etc. Now let us move on to the dynamics of simple harmonic motion, where we'll understand the nature of the restorative force that is responsible for SHM. So we know from kinematics, if we have an SHM given by the relation A sine omega t plus phi, it means that the acceleration or d2x by dt square is minus a omega square sine omega t plus phi, which means that the relationship between these two quantities is given by d2x by dt square, which is minus omega square x. So when we convert this to dynamics, so that means that if m is the mass of the body or the particle, in SHM, okay, then the net force acting on it so the net force is given by minus m omega square x. Okay, or we can write this equation as F is equal to minus kx, where k is some kind of a positive physical constant. So this tells us the nature of, so this is the what we call the dynamical condition for SHM. That at the point x equal to 0, the net force should be 0. And at any non-zero value of x, the net force is proportional to displacement but opposite in direction. That means it is a restorative force that is proportional to the displacement in magnitude. Okay. So you'll see that any system that dynamically follows this condition or dynamically satisfies this condition, whatever type of force is acting on it, it can be electrostatic, it can be elastic, it can be forces applied by some kind of an external agent artificially creating these forces. But if the force condition satisfies this statement, then by definition that system will be simple harmonic in nature, with x equal to 0 as the stable equilibrium or mean position. So just make a note of this point first, then we'll continue from here. So of course that constant k looks just like a spring constant, but the point is, yes, if it is a spring mass system, then k will be nothing but the spring constant or the stiffness of the spring. Even if it is not a spring mass system, the quantity k will be an equivalent of a spring constant. That means it will be such that the net force is proportional to x but opposite in direction, and the proportionality will be a physical constant of the system, which is then called the force constant. So the force depends on that proportionality constant. So it has the same dimension as the spring constant, but it can be as a result of some other type of force also. It need not always be because of the elasticity of a spring. Okay, so we can now describe this in words by saying that any one-dimensional system with x equal to 0 as an equilibrium position such that a restorative force proportionate to displacement from the mean position acts is going to perform SH. In fact, we can add this as it's a stable equilibrium position, because obviously we're talking about restorative force. Okay. So here the quantity K is called the force constant. It is a physical constant for the given system, such that the dimension of K is dimension of force per unit length, and so the time period of oscillation is inversely proportional to square root of this force constant. Further, the time period capital T or frequency F equal to omega by 2 pi depends for such a system. This depends only on the force constant and the inertia, that is the mass of the body. It is independent of initial conditions. The initial conditions, you will remember, determine the value of amplitude and phase constant. We've done that in the derivation of the equation of SHM, when we had started with the differential equation d2x by dt square is minus omega square x, and we went backwards integrating it twice to prove that x will always be a sine omega t plus phi. So there we had seen that the definition of a, or the amplitude, in terms of initial state, was that it is square root of x naught square plus v naught square by omega square. Similarly, the definition of the phase constant phi is tan inverse of x naught divided by v naught by omega. So these two parameters amplitude and phase constant, they are the ones which depend on the initial conditions. Whereas the time period or frequency of oscillation does not depend on the initial conditions. It's independent of that. So we'll understand these aspects with an example very soon. So given f is equal to minus kx, it implies that d2x by dt square is minus omega square x, where omega square is k by m. So that implies that x is equal to a sine omega t plus phi, where this amplitude is what is determined by the initial conditions. And the phase constant is determined by the initial conditions. So these two terms, amplitude and phase constant, they are determined by the initial conditions, whereas the time period is not. Yeah, I have actually written in detail what these notes are. Okay. So we have seen that the condition for SHM in terms of acceleration we had seen earlier was this d2x by dt square is minus omega square x. Now if you apply Newton's second law, net force is equal to mass into acceleration. That gives you this condition on force. So that is what the first note is about, Ansh. It's explaining that dynamical condition of SHM. That what is the condition about the force in any system if it has to perform SHM? This is the condition that if x equal to 0 is a stable equilibrium position such that restorative force always points towards the mean position. So there is a restorative force proportional to displacement that acts, then it is going to be a system that performs SHM. So that is the first point of explanation. The second point is that in this equation, f is equal to minus kx, where k is the force constant. The value of omega, or accordingly the value of time period, then only depend on k and m. So they are independent of the initial conditions x naught and v naught. Okay, so hope the point is fully clear now. Okay, so given that we know the type of force that is acting in a system, it satisfies the given condition that f is equal to minus kx. Then from the force constant, there is the value of k and the mass of the body. We know that time period and omega should be how much, because they don't depend on x naught and v naught. They only depend on these two properties, m and k. Whereas what actually affects, or what is affected by the initial state x naught and v naught, that is actually the amplitude and the phase constant. Okay, so now we will apply this dynamical condition concept to the most standard and most obvious example of simple harmonic motion. The most intuitive example of a simple harmonic motion is a spring mass system on a horizontal surface which is smooth. So we move on to spring mass systems. And their simple harmonic motion. So the first example we start with is a simple single spring block system on a smooth horizontal surface. Let's start with this. Suppose this is some kind of a smooth, frictionless horizontal surface, and there is a rigid wall on one side. It's a fixed wall. This is a smooth horizontal surface. Now we placed a block of mass m and we have attached it with a spring of constant k. Now we can see here that if this is the position where the spring is at natural length, then from this position, whether we give it a positive displacement or a negative displacement, whichever be the case, there will always be restorative force, which is proportional to displacement and opposite in direction. So it will always have that relationship that the net force acting. So this is, you can see the equilibrium position. So the net force on the body is zero here. Okay. But compared to that, if you look at these two other situations, you can see here that if this block has been given a displacement x in this direction, it will develop an acceleration in the opposite direction because the spring will be stretched. So it will apply a tension of kx. Or if the block on the other hand is pushed towards the left, so it has a displacement now which is in this direction. So you'll have an acceleration which is in this direction. So because the surface is frictionless, so this is the net force. This tension will be the net force. And d2x by dt square is opposite to x. So as a vector equation, we can write this as f is equal to minus kx. So this example, x is positive, so f is negative. In this example, x is negative, so f is positive. And we can see that this is the equation of SHM with the time period of 2 pi under root m by k. So this is the most obvious and the simplest example of a simple harmonic system, because the net force is just nothing but the spring force that is coming from a single spring which is on a horizontal surface. So the net force is nothing but minus kx, where k is nothing but the spring constant or the stiffness of that single spring. It's something very, very simple and uncomplicated. Okay. So now what we'll do is, suppose now in this we treat it like an example. So for this horizontal spring mass system. Okay, given that suppose the spring constant is 25 Newton per centimeter, and the mass of the block is 4 kilograms. Find the time period, angular frequency, and equation of SHM with amplitude and phase constant. If initially the spring is extended by 2 centimeters and the block released from rest. And the B part of the same question, initially the block is at the mean position and is acted upon by a sharp impulse of J equal to 0.8 Newton second towards the left. Okay, so now let us understand how we'll implement from the dynamical condition the formula for omega and time period, and from the given initial conditions the value of amplitude and phase constant, and from that we should be able to write the equation of SHM and understand how the displacement of the block from the mean position will vary as a function of time, how its graph will look and all these things, how much amplitude, phase constant, all these things it will have. Yes, very good, Aman. That's correct. So we can see straight away from we have already developed the formula for omega and time period. So in this case, it is 25 into 10 raised power 2 divided by 4 kg. So omega is 25, right? Radians per second. That's correct. 50 by 2, 25. Okay. So time period is 2 pi by 25 seconds. something like 0.25 seconds. Okay, now in the A part, what is happening is that this is the initial condition. We are releasing it from rest. So the amplitude will become 2 centimeters and the phase constant become pi by 2. So this is the first part. That is what x will look as like as a function of time. Okay, so remember that the value of omega is independent of initial conditions. Depends on physical properties, spring constant and mass of the body. Okay, now similarly, please determine the equation of SHM for the second one with the amplitude and phase constant. You have to apply the impulse momentum theorem to understand how much the initial velocity is. Yes, Aman, your answer looks correct for amplitude and phase constant. No, phase constant is not correct within the second one. Be careful. Phase constant is not minus pi by 2. And I think you have made some mistake of unit for the angular frequency. So hope it is clear now. Omega is same for whatever part, okay, A or B, because it only depends on K and N, which is the same for both the parts. Okay, so what about the second part, people? Nobody's got the answer. It's very simple. In the second part, what is happening? Initially, the block is in the equilibrium position, so x is equal to 0. But you're giving it a sharp impulse in this direction at t equal to 0. So at t equal to 0, it will develop a velocity in this direction. So the V naught will be minus of whatever impulse you applied divided by the mass. If you're taking the sign convention that your x-axis is like this, okay, and your x naught is 0. So just substitute the values now. What was the impulse you were applying? It was 0.8 Newton second, and the mass of the block is 4 kg. So minus 0.2 meters per second, or minus 20 centimeters per second. That is the V naught. Okay. And omega doesn't change, of course. Omega is root k by m, which we have seen is 25 radian per second. So the amplitude, which is square root of x naught square plus v naught square by omega square here, just becomes 20 by 25 in centimeters. Okay. So the amplitude becomes 0.8 centimeters. Okay. And the phase constant becomes tan inverse of 0, which could be either 0 or pi, but in this case, v naught is negative and x naught is 0, which means that cos phi should be negative and sin phi should be 0, which means that phi should be pi. So my equation of SHM is 0.8 sin 25t plus pi, or x is equal to minus 0.8 sin 25. Here again, x is in centimeters, t is in seconds. So the graph of x versus time this time, for this case, will look like this. Starting from the mean position, but it's going towards the negative side. So at quarter of the time period, would have reached minus 0.8. So this is how we have to make use of the initial conditions along with the dynamical condition. Okay. The dynamical condition was same for both the parts because you're not changing the physical properties of the system, that is the spin constant and the mass. Okay, so I hope both the parts are clear to all of you. Please ask me in case of any doubt here. Okay, let's move on to another question. related to this kind of system now. Just a moment, people. Just give me a moment that whiteboard software needs to be rebooted. Okay. Yeah. So the next question we'll discuss is going to be an interesting variation of this. So we have this situation now. Okay, so this is a smooth surface and all that. Now, right now, this is at natural length. And this is at a distance of 2 centimeters. So given that the spring constant is 4 Newton per centimeter, the mass of the block is 1 kg, the horizontal surface is frictionless. Now, the block is pushed left by 4 centimeters from the position shown above, and released from rest. So find the time and speed at which it impacts the wall on the right for the first time. If the collisions are perfectly elastic every time, then show that the system will be periodic. So show that the system will be periodic and find its time period. On the other hand, if E is equal to 0.75 for the first impact. Then find the maximum compression for the spring after the first impact. Okay, so people just try out this question. So since it is also asking about the time taken for the system, okay, so you cannot just apply work energy, conservation of mechanical energy here and apply the and collision theory and get the answers for everything. You have to apply the concept of simple harmonic motion also.
Teach. सीन चेंज करेगा बस पूरा दिखाना चाहता है मुझे सका तो दबाना चाहता है पर मेरे पास तेरे लिए बहुत सारी सच्चाई है ऊपर से शब्दों का चाटा है थोड़े के हाथ में आज के रात में करो पर बाद में करो मैं तेरी पोपली को सांस में गया मैंने डाला मैंने मैं ढूंढने को ज़माने जब वफा निकला ढूंढने को ज़माने जब वफा निकला पता चला कि मैकेनिकल है ना मैकेनिकल है पेज वापस तो फिर से रहेगा क्या इस तरह फ्लॉप होता अब क्या करेगा हाँ तो पहले से पहले क्वेश्चन बनाएंगे तो ये ऊपर से शब्दों का
Okay, so let's take a look at this section. So here what is happening is that at t equal to 0, you are compressing to the block against the spring. Let's say this was the mean position. So giving it an initial displacement of minus 4 centimeters and releasing it from rest. So once again, the time period is 2 pi under root m by k. Spring constant was given as 4 Newton per centimeter. So this is becoming pi by 10 seconds or approximately 0.314 seconds. This is the time period. Now these are the initial conditions. So the amplitude this time is 4 centimeters, but the initial phase constant will be how much? Minus pi by 2, because x naught is negative and v naught is positive. So hope this is clear to all of you. So x as a function of time will be minus 4 cos 20t, where x is in centimeters, t is in seconds. So what will happen now is that this is where the block was at t equal to 0. And this is where the wall is at plus 2 centimeters. So if it comes and hits the wall at some time t1 with a speed v1, you can see that at t equal to t1, impact for the first time, x should be equal to plus 2 centimeters. Okay. So now you can understand this. The easiest way to find the time would be just go back to this thing, projection of UCM. Very easy way of understanding this. So if we take this as our x-axis, at t equal to 0, it is at minus 4. Okay. I was going with this omega. Now at time t1, it should be at plus 2. So it should be here. So you can see that the angular displacement is this. Okay. So this angle here, you'll see, is pi by 6. Okay. So omega t1 has to be pi by 2 plus pi by 6 or pi by 3. Okay. So time t1 has to be equal to capital T by sorry, 2 pi by 3. My mistake. So it has to be capital T by 3. Okay. So this is the time when the first collision will happen. And speed v1 will be minus 20 into 4 sine 20 t1. Okay. Now this cos omega t1 minus half, na? So sine omega t1 become root 3 by 2. So v1 will be sorry 40 root 3.
So it should be cos 20t.
Sorry, come again, beta.
It should be cos 20t1.
Nee, x is minus a
Okay,
cos
okay,
omega
okay.
t, na?
Yeah.
So v is getting it, na?
Yes.
It's like this. So v over here is plus a omega sine omega t, or you can say x is e sine omega t minus pi by 2. So v is a omega cos omega t minus pi by 2, which is the same thing as this. Okay. So this should be like done without too much difficulty, this type of situation. And the easiest way, as I showed you, is instead of doing all this calculation manually, that just understand it on the projection of UCM. This is our x-axis here. Okay. Now let's come to that part, that so we have got the time at which the first collision is happening, and we have got the speed at which the first collision is happening. Now the next part is we wanted to show that the motion will be periodic and find the time period if the collisions are perfectly elastic. If repeatedly the collisions with this wall are perfectly elastic, then show that the motion is periodic and find its time period. So just remember what happens in a perfectly elastic collision with a rigid wall like this. It rebounds with the same speed. No? Okay. So actually the answer is right in front of you. Okay, for the second part. Just try to figure it out and tell me how much will be the time period. You'll realize it's a periodic motion because there's no loss of energy happening. No? How will the motion look like after the impact? Just after impact, its velocity will be minus v1. No? Not 2 times capital T beta, because it doesn't complete that cycle. So Aman, you have to be just a little bit careful in answering this last part. So see, t equal to 0, it started from just a moment. Yeah, t equal to 0, it started from x naught equal to minus a, that is, okay, and v naught equal to 0. Then at quarter of a time period, it's at x equal to 0, b equal to plus a omega. Then at this time t1, which we saw, which was capital T by 3, in fact, it was at x equal to plus a by 2, and its velocity of impact was therefore plus root 3 by 2 a omega. Okay. Now, if the collision is perfectly elastic, what will happen immediately after that? You just reverse its direction, rest everything remains the same. Okay. So just after impact, neglect the time of impact. So the time from the beginning is still t by 3 only, but its speed has become like this now. Okay. So from here, it will again reach this position at t equal to t1 plus t by 6, having a velocity of minus a omega. Okay. And then it will come back to this position. It will go in this direction, at a time of how much? At a time of t1 plus t by 6 plus t by 4. Okay. So that's another t by 3. So this time will be actually 2t by 3. So, from here to here is now half cycle. And then back from here to here is the second half cycle. So this will be the net time period. So this will be the period. It will be 2 times 2 by 3 of this will be the time. So if you visualize the x versus t graph, you'll see that it's not an SHM because it doesn't complete the cyclical motion. Okay. But what it does is, now instead of reaching this point, you would have completed and come back here. Now the impact happens here. So it, like this part of the motion which would have happened, now this happens. And then this whole thing repeats. These are all the impacts. This is the first impact, the second impact. So this is the new time period. So it is like a truncated SHM. Like, instead of the SHM completed, it's just this part is removed in the SHM. And this is just brought here. Okay, hope this is clear, people. So mind you, this will not be an SHM. हाँ, because देखो यहाँ पे क्या हो रहा है ना, it is going from like just visualize this way, no? Okay. This is where it started from at t equal to 0. Okay. Then this is where the first impact happened. Okay. And then just after the first impact, it's where it's here. No? So now it's coming down. So this is just after first impact. So t equal to t1, and it jumped from this to this because the shadow, the projection is going up and then coming down. Okay, and then this is where it is at the mean position. So this is t equal to t1 plus, now this is how much? It's pi by 6. Oh, sorry. So that will be t by 12. My mistake, not t by. This one will be it's like 1/6 of the full cycle from here to here. So that is why my t1 is actually what it is, t by 4 plus t by 12. So it's t by 3. And then this time, okay, let's say this is t2. So that t2 t by 3 plus t by 12. And then finally, it's back here. Let's say that is t prime. Okay. So that is, this is the time period. The time period is t2 plus t by 4. So it is t by 3 plus t by 12 plus t by 4. So it's 2t by 3. So in my diagram, this was t by 4. Then this is when the first impact happened. Then this is where it is back to mean position from the first impact. And this is t prime. Okay. So the motion is not an SHM. It is like part of SHM, but incomplete. But it is periodic and it has a time period of this much. So hope the method of calculation is clear in this case, people. Okay. Aman, you have made that correction. No? It's not t1 plus t by 6, but t1 plus t by 12.
So can
It's
you
a phase
scroll
angle of
bit
pi by 6. No? So, okay.
up? So can you scroll a bit up?
Yeah, sure. This part, Kevin?
Yes.
Okay. So hope all of you have understood the method of visualization that I have used using the this thing, projection of UCM. It's much easier to understand when it will hit the wall. That on the UCM partner, the phase angle is going from minus pi by 2 to plus pi by 6. So it's very easy to understand that is covering a phase of pi by 2 plus pi by 6. That is 2 pi by 3. So obviously the time will be capital T by 3 because the phase angle is 2 pi by 3. So that omega T1 is 2 pi by 3. So T1 is obviously capital T by 3. Okay, done with this?
Yes.
Okay. Now this cyclical time part is clear, no? Okay, now come to the last part. Okay. Last part was that if instead the collision happened with, if the first impact happened with a coefficient of restitution 0.75, okay, then find the maximum compression of the spring. Okay. Now this part actually you can do by work energy also, because it's just asking for maximum compression. It's not asking at what time the compression will be maximum. But try to also understand it if you can from the SHN method. Okay, let's try out this part now. So just before impact, I'm seeing that it is having a speed of root 3/2 a omega, where a was 4 centimeters. Okay, omega was 20 radians per second. At that time t1. Now if the coefficient of restitution is 0.75, then just after impact, and the position at this point of time is how much? It is plus a/2. Okay. Now just after impact, it will have a speed which is minus of e times v1. So that is 3/4 of this now. So 3 root 3/8 a omega, but the position is still plus a/2. Okay. So now if it goes on the other side to maximum compression after some time, so this was the mean position. This was, okay. Now it goes to x equal to minus minus some new amplitude. So it will be a prime. Okay. where its V becomes 0. So you can see that the energy over here and here has to be conserved. That's one way of understanding it. So half m v2 square plus half kx2 square has to be equal to half k a prime square, where a prime is the new maximum compression. Now m omega square is the same thing as k. Okay. So we can see that 9 by 16 a square plus a square by 4.
So we'll put V2 in there.
Oh, wait. There's also a root 3 by 2 factor. Okay. Wait a second. This V2, which is there now, this V2 I'll write in terms of this, that it is minus of 3 by 4 into root 3 by 2 a omega. Yeah, so just forgot that root 3 by 2 factor. I'm just showing you a convenient method of solving this. Okay, so I've got this is okay, half m. So half m 3 root 3 by 8 a omega whole square. This one. So this will be 3 root 3 by 8 capital A whole square instead. So instead of 9 by 16, this will be 27 by 64, right? 6 square. And half k is cancelled everywhere. So that will be a prime square. So a prime will be a into square root of this thing. 27 by 64 plus 1 by 4. So when you work this out, you'll see that obviously this a prime is less than a, but this will be the exact value. So we are still using work energy, but I'm using it in the language of SHM, which makes it a little bit easier. And remember, capital A was 4 centimeters. So this. So you'll see that root 43it is around 6.6 approximately. So this is something like 3.3 centimeters approximately. That is what our A prime will. Anyhow, so hope this is clear, people. Okay. Now we move on to vertical spring mass system.
So can you scroll up once? Just once.
Yeah. That's just work energy. You can do a normal work energy type of calculation also instead of writing V2 in terms of A omega and all that. But this just makes it more convenient because factor just gets cancelled out.
Yes.
Okay. Just a minute. Before we come to vertical spring mass system, we'll also discuss mechanical energy of SHM through the example of the horizontal spring mass system, and then we will see how that translates to every system actually in SHM. So in the case of horizontal spring mass system, if at any particular point of time the spring is having either an extension or a compression and the block is having a speed in either direction, then kinetic energy plus potential energy is conserved, because for the system, that is the spring plus the block, we have no work done by external force, no work done by non-conservative forces. So mechanical energy is conserved. Okay. So half mv square plus half kx square is the mechanical energy. Now here x is in general a sine omega t plus phi, and v is in general a omega cos omega t plus phi. So you can see that as a function of time, the potential energy is half ka square sine square omega t plus phi, and the kinetic energy is half m a square omega square cos square omega t plus phi. So that can be written as half ka square cos square omega t plus phi, because remember omega square is k by m. Okay. So the total mechanical energy therefore becomes half ka square. Okay, so putting this back over here, we can see this important thing that the potential energy at any point of time is the total mechanical energy into sine square omega t plus phi, and the kinetic energy at any point of time is the total mechanical energy into cos square omega t plus phi. So here, of course, we are talking about horizontal spring mass system. So K is not just the force constant, but it's actually the spring constant or the stiffness of the spring, and M is the mass of the block. Okay, but we will see that even in a general situation where K is a force constant for whatever type of force, and M is the inertia of the system, this kind of formula will still work. Okay. Okay, so another aspect of this is now, if you look at the time variation of energy in the system, then for example, if we have a situation where x is E sine omega t, I've taken the phase constant as 0. So my potential energy will look like this, look like the sine square function, where in one cycle of SHM, it would have changed twice. Okay, so this is the potential energy, whereas the kinetic energy would be the cos square function. So that would look like this. And the total mechanical energy is going to be the sum which is constant. Now also, potential energy is half kx square. Kinetic energy is half mv square. Now v square is a square omega square cos square omega t plus phi in general. So that can be written as a square omega square 1 minus sine square omega t plus phi, which can be written as omega square into a square minus x square. So this can be written as half k into a square minus x square. So m omega square is the same thing as k. So the other aspect of this now is that if we look at the variation of energy with respect to position in an SHM, that look like a quadratic graph for each type of energy. So this is my plus A and this is my minus A. So the potential energy function will always look like the half kx square term, which is going to have maxima at the extreme positions, 0 at the mean positions. And so this is potential energy. The kinetic energy will be proportional to a square minus x square. So it's maximum at the mean position, while the total mechanical energy is constant. So these are important for kinetic energy and potential energy as a function of x or the position. And the above ones are important as kinetic energy and potential energy as a function of time. We've written these. Okay, so this is all part of standard properties of SHM, and you can say it's part of dynamics only because after all, work energy comes, its derivation comes from dynamics only. You have the equation F net is equal to MA. You take dot product with ds on both sides and integrate, and you get your work kinetic energy theorem. And then you infuse the concept of conservative force and potential energy, and you get the work energy theorem from that. So it's all part of dynamics. Okay, now we'll just take a few minutes because in between my connection had got frozen, so I missed out some time. I just want to like complete up to the target for today, which is vertical spring mass system. So I think it's okay if I take about 10 minutes extra, right? I mean, non-integrated students will be having some class not before 6:15, I guess, right? So the difference between the vertical spring mass system and the horizontal one is the referencing of this thing, equilibrium position. It is not the position at which the spring is at natural length. It's a position where the spring has a certain amount of stretch. So if this is our equilibrium position, or what in language of SHM we call mean position, then the spring is having a certain amount of stretch over here. So what we will do is we will use two different parameters. The parameters that we will use, X will be for extension of spring. So obviously positive means extension and negative means compression. Whereas we will use another parameter Y, which will be the SHM parameter, which is going to be the displacement from mean position. So our mean position will be taken as y equal to 0. Okay. So this is where our y-axis will start from. This will be our y equal to 0 position, and this will be the sense of our y-axis. Okay. So from here we can see that if we take the block to a displacement y above, okay, now the spring's compression has become less. It might have even become, extension has become less. Okay. So if the block has been displaced upwards by a positive y, you can see it will have a downward acceleration. Okay, because x here is x naught minus y in this case. Okay. So here equilibrium means acceleration is 0. Okay. So kx naught is equal to mg. This is our first equation. Okay. Here, what is happening? Kx will become less than mg because x is less than this. So it has a downward acceleration. So we have mg minus kx is equal to ma. So mg minus k into x naught minus y is equal to ma. So if we compare this equation with the first one, we can see that we'll get our SHM equation. Now you substitute this here. That's giving us our equation that ky is equal to ma and a is minus of d2y by dt square because it's opposite in direction. So it's giving us our required SHM equation. So d2y by dt square is minus k by m into y. So this is an SHM with omega equal to root k by m, time period equal to 2 pi and root m by k, and y will be a sine omega t plus phi, where again a is square root of y naught square plus v naught square by omega square. Like that. Now this can also be shown from the other side. That is, if we give more compression, if we give more extension from the mean position. So this is our E equal to 0 position. This is L plus X naught. Okay, so this is our Y equal to 0 position. Now from here, we pull it down. Then we are giving a negative Y displacement. But the acceleration will be positive. And again, you can see that this time still the same, but Y is negative. Okay. So X is greater than X naught. So Kx is greater than Vt. So when you apply this, this will give you the same equation, give you the same condition. So it's just like a recalibrated SHM. It's doing SHM, but not about the position where X is 0 for the spring, but about the position where X is equal to X naught, that is mg by K for the spring. So you take that position as your origin for the SHM parameter. You just keep two separate parameters. X is the extension of the spring. Y is the displacement from mean position. Y equal to 0 is the position where the block is having equilibrium, not the position where the spring is relaxed. So that is how a vertical spring mass system works out. Okay, so hope this is clear, people. With this, we conclude today's session. Now you can attempt all questions related to spring mass systems and SHM from HC Verma. You will see questions where there are various combinations of springs, series, parallel combination, then some with springs connected in different ways. So some constraint relation kind of things will have to be worked out. So we'll discuss some of them as doubts in the next lecture. But with this information, you should be able to solve or attempt any question which has a system of springs and mass which is performing SHM. Okay, so that's it for today's session, people. Thanks for attending. Wish you all the best.